Every sunrise feels like a promise, a quiet reassurance that no matter how chaotic the world becomes, the sun will return. It has always been there, rising with mechanical precision, painting the horizon in molten gold, scattering shadows and fear alike. But what if that comforting ritual is nothing more than a fading heartbeat? What if every dawn is not a promise, but a countdown? Imagine opening your eyes tomorrow and realizing the sun you've trusted for all of human history is already dying. At first, the idea feels absurd. The sun is ancient, powerful, invincible. It has burned for billions of years and will burn for billions more, or so we like to believe. Yet even the mightiest flames run out of fuel. Even stars have expiration dates, hidden beneath their brilliance. The irony is almost cruel. The very force that gave us life also carries the seed of our annihilation. We orbit a slow-burning fuse, pretending it's eternal. But eternity is an illusion our fragile minds cling to. Watch the horizon at dawn, and you can almost sense it. Light creeping over the edge of the world, like a cautious whisper. For now, it feels gentle, harmless. But beneath that beauty, inside the star's fiery heart, hydrogen atoms slam together at unimaginable speeds, tearing themselves apart to fuse into helium. That delicate balance between outward radiation and inward gravity is what keeps the sun alive. It is also what keeps it from collapsing or exploding. The moment that balance falters, the sun will begin its death spiral. The thought chills more than the coldest night. If you stood still and truly watched the sun rise, not glanced, but watched, you'd notice how familiar it is. Too familiar. Its constancy has lulled us into arrogance. We set our clocks by its rhythm. We define time itself by its path. We rarely ask if it will keep going, because deep down, we fear the answer. Humans are not wired to wake each morning wondering if the sky will ignite. And yet, what if it did? Imagine this. One dawn, the first clue appears. A slightly brighter glare at the horizon, subtle enough that no one notices. By the next year, the light seems harsher, the heat heavier. Scientists argue over measurements, dismiss the anomalies as instrument errors. Meanwhile, the sun grows restless. Solar flares lash farther. Sunspots multiply like scars. And then, one morning, the sky doesn't pale gently. It erupts. The blue is drowned in molten white, as if the heavens themselves are on fire. Mountains cast no shadows. Oceans shimmer in steam. Cities vanish into silhouettes, then into nothing. It would be over before most people understood what was happening. The unsettling truth is, this nightmare isn't just fantasy. It is the end every star eventually faces. The sun appears still, but inside it is changing with each heartbeat. The same nuclear fire that keeps it steady is also draining it. Like a candle burning down from the inside out, its apparent calm hides a deep, inevitable decline. And the scariest part? We can't know the exact timing. Our calculations give it 5 billion more years. But calculations are only as perfect as the assumptions behind them. What if the sun isn't following the schedule we expect? We know stars die because we've seen their corpses. White dwarfs, neutron stars, black holes, remnants scattered like cosmic gravestones. Many of them were once suns like ours. Some seemed stable right until their collapse. That's the haunting possibility, that visible calm doesn't mean safety. By the time we notice visible warning signs, the process could already be unstoppable. Our sun could be older in spirit than we realize, its clock ticking faster, its heart weakening invisibly. There's another unsettling layer. The sun doesn't just give light. It anchors the balance of everything: oceans, winds, climate, biology. The slightest deviation in its output could fracture our entire world. A mere 1% increase in luminosity would boil away Earth's oceans over geological time. A sudden surge of flares could fry our satellites, erase our power grids, plunge us into centuries of chaos. The sun doesn't need to explode to kill us. It only has to stumble. And stumbling stars often do so quietly. Not with an explosion, but with a subtle brightening, a whisper of instability. The sun's magnetic field could grow erratic. Its fusion rate could speed up fractionally as the core contracts. That alone would accelerate its aging. Yet, to the naked eye, the star would look the same. The sky would still be blue. Sunsets would still paint clouds in orange and rose. We'd go on planning futures under a dying star, blissfully unaware. This is the paradox that makes the idea so chilling. The sun's death will begin invisibly, long before we see it. The photons warming your skin today may have been born hundreds of thousands of years ago, deep inside the core, slowly crawling outward through dense plasma. The light you see is history, which means what's happening right now in the heart of the sun. We won't see it until long after it has begun. The star could already be unraveling, and we'd be smiling up at its ghost. Human arrogance resists that thought. We measure things in human lifetimes, decades, maybe centuries. The sun seems so slow that we treat it as frozen, but stars live on timescales that mock our sense of time. What looks stable on a human scale can be collapsing on a cosmic one. Imagine ants watching a glacier. To them, it never moves until it crushes their world. We may be those ants, and if the countdown has begun, we will have no reset button, no backup star. The sun is our singular lifeline, the engine of all warmth, the clock of all seasons, the power source for every heartbeat and breath on Earth. Without it, photosynthesis halts, temperatures plunge, the atmosphere crystallizes, and our blue planet becomes a silent sphere of ice orbiting a corpse. There would be no warning siren, no global emergency broadcast. Just one day, less light. The fear isn't just that the sun will die. It's that it might do so faster than we've believed. Our models are based on averages. On other stars we assume are similar. But stars are individuals. Some age gracefully. Others spiral into chaos unpredictably. Slight changes in rotation, magnetic turbulence, or chemical mixing can warp their timelines. What if our sun has hidden instabilities we haven't detected yet? What if it has already crossed a threshold, quietly slipping from midlife into decline? Think about how blind that makes us. We gaze at it with telescopes, measure its surface storms, monitor its flares, yet we cannot see its core directly. We infer its age from models, not from certainty. The sun could be living on borrowed time, and we'd only realize it when it starts to burn faster, swell outward, and turn the blue sky white. By then, the countdown would be irreversible. This thought scratches at something primal, the fear of losing the most fundamental constant in our lives. Every culture, every language, every calendar we've ever made depends on the sun. It is our ultimate symbol of stability. The day it fails will shatter more than physics. It will shatter the idea that anything endures. That realization is almost unthinkable. And yet, maybe that's why it matters. Because pretending it's impossible won't stop it from happening. And if it did begin, if tomorrow's sunrise was the last, we would not be ready. Civilization would face its own mortality overnight. Economies would implode, governments collapse, families scatter. People would cling to meaning or abandon it entirely. Some would run, some would pray, some would simply stand outside, watching the sky blaze, knowing there was nowhere left to go. No one can prepare for the death of the sun. You can only decide how you will meet it. Maybe that is why this question pierces so deeply. Because it is not just about astronomy. It is about us, about the way we drift through days like they're infinite, convinced there will always be another dawn, another chance. The sun's apparent immortality feeds our own denial of endings. But everything ends, even stars, especially stars. And when you know that, every sunrise becomes something else. Not routine, not guaranteed, a fragile miracle, a fleeting heartbeat, a warning and a gift at once. So ask yourself, what would you do if this was the last one? Would you scream at the heavens or sit quietly and watch? Would you try to save the world or simply savor it? Because somewhere, someday, someone will wake to that final dawn, and they will realize the sun was dying all along. Time is a strange illusion. To us, centuries feel endless. Civilizations rise and fall in the span of a few thousand years and call themselves eternal. Yet to a star, 1,000 years is nothing more than a sigh. The sun has watched ice ages come and go like passing seasons, witnessed continents drift like lazy clouds, and seen entire species blaze into existence and vanish like sparks. It seems immortal because it moves on a timescale so vast our minds collapse trying to measure it. But immortality is not real. Even this colossal beacon of fire is not timeless. It has a life story, a birth, a fragile middle age, and an inevitable end. We only think it's frozen in time because we've never seen it blink. Roll the cosmic clock backward, and the sun we see each morning dissolves. There is no light, no heat, no gentle sphere in the sky. Only a cold darkness filled with drifting gas and ancient dust. The leftovers of dead stars scattered like ashes across a quiet spiral arm of the Milky Way. For millions of years, that cloud floated aimlessly, a silent sea of hydrogen and helium peppered with heavier elements like carbon, oxygen, and iron, gifts flung out by ancient supernova. Nothing about it hinted that a future world would bloom from its dust. It was simply debris, forgotten and still, until the silence broke. Somewhere nearby, a star died violently. Its death scream, an expanding shock wave, raced through the void and slammed into the cold cloud. Like a cosmic hand squeezing a sponge, the blast compressed the gas, forcing it to clump together. Gravity took hold. The denser a region became, the harder it pulled on itself, spiraling inward like water down a drain. Dozens of knots formed inside the cloud, each collapsing under its own weight. One of those knots would become our sun. As the knot shrank, it spun faster, flattening into a swirling disk like a cosmic whirlpool. The center grew hotter and denser with each heartbeat. For millions of years, it was only a faint ember buried in the dust, a protostar glowing dimly in infrared. Matter from the surrounding disk rained inward, crashing into the core and heating it further. Powerful jets of plasma blasted from its poles, carving holes through the collapsing cloud. Slowly, the chaos quieted, and then came the moment that changed everything. When the temperature at its heart passed 10 million degrees. At that threshold, something miraculous began. Protons, once fiercely repelling each other, were forced so close that they tunneled through their mutual resistance and fused. In a chain reaction, hydrogen nuclei combined into helium, releasing bursts of pure energy. The star ignited. For the first time, light not borrowed but self-forged burst outward. The fusion furnace was lit, and the sun was born. It was not yet the sun we know. Its surface still shrouded in residual dust, it pulsed erratically, shedding the last gas of its cradle. But fusion stabilized its heart, and the newborn star began to push back against gravity with perfect balance. Radiation streamed outward. The disk of leftover material cooled and clumped into planetesimals, grains becoming rocks, rocks becoming worlds. Out of that scattered debris came Mercury, Venus, Earth, and Mars. While our planet was still molten and hostile, the sun was settling into its longest chapter, the main sequence. On the main sequence, a star lives in equilibrium. Gravity tries to crush it inward. Fusion pushes outward. For our sun, this balance has lasted 4.6 billion years. Every second, about 600 million tons of hydrogen vanish into helium in its core, converted to light through nuclear fusion and released as photons. Those photons spend hundreds of thousands of years ricocheting outward through dense plasma before breaking free from the surface, racing across space and touching your face as warm sunlight. It feels eternal because it is steady, so steady that all of life has evolved around its constancy. Plants time their growth to its cycles. Animals, including us, anchor their rhythms to its rise and fall. It is the heartbeat of the solar system, but even this balance is fragile. Inside the core, hydrogen is steadily disappearing. Each reaction leaves behind helium, which sinks inward because it is heavier. Slowly, atom by atom, the fuel tank empties. Nothing in the sun's outward appearance reveals this. The sky does not dim, the seasons do not falter. But deep inside, the proportions are shifting. Every ray of sunlight is a receipt of fuel spent and gone forever. Picture an hourglass. The sand at the top is hydrogen. The sand piling up at the bottom is helium ash. The stream is steady, constant, reassuring. It lulls you into believing the flow will never stop. But the top half is shrinking, grain by grain. That is the secret timeline hidden inside the sun. The upper chamber is running out. Astronomers estimate it is halfway through its main sequence life. That means about half the hydrogen in its core has already burned away. In human terms, if the sun's life were a single 80-year lifespan, it would now be around 40. Middle-aged, stable, yet already heading toward decline. The fusion rate will subtly increase as the core contracts and heats up, trying to compensate for the dwindling fuel. That extra heat will slowly make the sun brighter, its light more intense. Earth will not notice it from one year to the next, but over tens of millions of years the oceans will begin to evaporate, the atmosphere to thin, and habitability will crumble long before the sun reaches old age. We will be gone not because the sun explodes, but because it quietly outgrows us. There is something unnerving about that. We imagine endings as sudden, explosive events. But the sun's death will come like aging, gradual, invisible, relentless. Even as it brightens, people will still wake to golden dawns, thinking nothing has changed. The illusion of permanence will be strongest precisely when the countdown is halfway over. And this is where the paradox deepens. The sun's stability is the very thing that blinds us to its fragility. It feels eternal because it changes too slowly for our eyes to catch. But physics catches it. Hydrogen depletion accelerates exponentially. As the core grows denser, fusion runs faster, burning fuel even more quickly. Like a person who sprints as they tire, the sun will race toward its finish. Eventually, about 5 billion years from now, the core will run out of hydrogen entirely. No new energy will be produced at the center to push outward. Gravity will win. The core will contract violently, heating as it shrinks, while the outer layers balloon outward into a red giant. This is the point of no return. The moment the sun leaves the main sequence and steps into its death spiral. When that transformation begins, it will happen far faster than its long, stable youth. The red giant phase will last only a few 100 million years, a brief, chaotic old age compared to its tranquil billions of middle life. The same star that glowed gently for eons will suddenly swell hundreds of times larger, likely engulfing Mercury and Venus, possibly even Earth. Even if our world escapes being swallowed, the sheer heat will vaporize its oceans and peel away its atmosphere. Long before the sun physically touches us, it will kill everything we know. And then, even that chaos will end. After the helium in its core is spent, the sun will not be massive enough to ignite carbon. It will shed its outer layers like glowing petals, leaving behind only a tiny, hot core, and white dwarf about the size of Earth, glowing faintly as it cools over trillions of years. The planets will be gone or frozen husks. The solar system will be a graveyard orbiting an ember. The star that lit the world will become a ghost. All of this is already written in physics. It will happen. The only unknown is timing. We assume the sun will follow the average pattern for stars of its mass, but averages can lie. Slight changes in its composition or internal dynamics could accelerate the schedule. We cannot open the sun and read its true fuel gauge. We infer its age by models, comparing it to other stars, and that uncertainty leaves a crack for doubt to creep in. What if it is older than we think? What if it is aging faster than expected, its halfway point already behind it? This is the hidden ticking clock. The sun does not show its years on its surface. It will look the same tomorrow, next year, next century, even as its heart quietly empties. Like a candle that seems steady until the final sputter, it hides its ending inside its light. And because we see only the light, not the decay, we are lulled into forgetting it is mortal at all. That is why understanding its timeline matters. Not because we can stop it, but because we must stop pretending it is immortal. Everything on Earth, every tree, city, ocean, heartbeat, is temporary because the star that powers them is temporary. We live in the middle of a long goodbye, and every day the goodbye grows closer. The sunlight that seems infinite is, in truth, borrowed. And one day, the debt will come due. If a star could grow old without showing it, how would we ever know? We look at the sun and see constancy. It rises each morning with the same steady blaze, sets with the same golden glow. Its face, dazzling and flawless from a distance, shows no wrinkles, no tremors. To the casual eye, it seems ageless, but appearances are the most deceptive mask of all. Deep inside, something may already be shifting, and the only question is whether we are clever enough or desperate enough to notice before it's too late. Aging stars do not announce their decline. They do not erupt in sudden fireworks or change color overnight. Instead, their decay is subtle, hidden in the fine print of their light. As they consume the hydrogen in their cores, their hearts grow denser, hotter, and faster burning. Paradoxically, this makes them appear even more vigorous to outside observers. Like a candle that flares brighter just before it gutters out, a star shines more intensely as its fuel dwindles. The tragedy is that this brightening is not a sign of youth. It is a fever, not a glow of health, but the flush of strain. And the nuclear fusion furnace inside our sun has been slowly turning up the heat. We know this not from guesswork, but from forensics. By studying stars similar to the sun at different ages, astronomers have stitched together an eerie timeline. Young solar twins shine a little dimmer, rotate faster, and unleash wild tempests of stellar wind. Older ones glow more brightly but spin sluggishly, their magnetic tantrums fading as their dynamos slow. Our sun fits eerily well into this middle-aged pattern, but the comparison also shows that it is already burning about 30% brighter than when it was born. That means the fusion in its heart is running hotter than ever. On the surface, nothing seems amiss. But beneath the calm light, the furnace is accelerating, and with every passing second, the clock speeds up. This brightening is not harmless. As the core shrinks and heats, the fusion rate climbs, producing more energy. That extra energy pushes outward, swelling the outer layers ever so slightly and making the sun's surface hotter. It is like a heartbeat growing faster under stress, quiet, invisible, yet undeniable. Earth's climate system delicately balances on this output. A rise of just a few percent would destabilize global temperatures, evaporate oceans, and sterilize the planet. The fact that the sun is brighter today than when life began is not a coincidence. It is a sign of age, but brightness alone cannot tell the whole story. The sun's core is where the real truth hides, and that core is contracting. Each time a fusion reaction turns hydrogen into helium, the heavier helium sinks inward. Over billions of years, it has piled up like ash in a hearth, weighing down the star's center. Gravity crushes it tighter, and the pressure squeezes the remaining hydrogen into an even smaller space. This makes fusion burn faster, which releases more heat, which makes the core contract further. It is a feedback loop, a slow spiral inward. The sun's outward calm hides an inward implosion already in progress. That shrinking heart is the surest sign that its youth is gone. We cannot see the core directly, but we can listen to it. Astronomers use helioseismology, the study of sound waves rippling through the sun's body, to map its interior. Like doctors with stethoscopes, they record subtle vibrations in the photosphere, the sun's visible surface. Those ripples bounce and echo through the interior, carrying clues about density, temperature, and motion. The patterns match what models predict for a star halfway through its life. A core heavier and more compressed than in its youth. Each oscillation is a heartbeat, and those heartbeats tell us the clock is ticking faster now. The sun is older than it looks. There is another, even stranger clue: its magnetic field. The sun's magnetism is not static. It churns and reverses in an 11-year cycle, flipping its poles and driving sunspots, solar flares, and coronal mass ejection storms. This cycle is born in a thin shear layer called the tachocline, where the outer convective zone rubs against the inner radiative zone, twisting magnetic field lines into knots. In young stars, this dynamo roars like a hurricane. As they age, their spin slows, the shear weakens, and their magnetic cycles grow quieter. But in recent decades, the sun's magnetic behavior has grown unpredictable. Its last few cycles have swung from strangely weak to surprisingly strong. Some researchers whisper that this might be an early sign of instability, a dynamo losing its rhythm as the interior structure shifts. Is that what we are seeing? Or is it just noise in the system? That question haunts solar physicists. If the sun's magnetic field is becoming erratic, it could mean its internal layers are starting to decouple, changing how energy and plasma circulate. Even small shifts could accelerate core contraction and trigger more violent flare activity. Imagine a heart developing an irregular pulse. It still beats, but each thump carries a hint of collapse. The sun's flares are that pulse, and lately they have thumped harder. The current solar cycle surged earlier and more intensely than models predicted. Space weather forecasters have scrambled to explain why. Is this just a natural fluctuation, or the first tremors of deeper change? That uncertainty gnaws because we have no second sun to compare it to. Every measurement we make is a snapshot of this one moment in its long life. To detect decline, we must hunt for whispers hidden in its light. And light does carry whispers. The solar spectrum, the fine fingerprint of colors in sunlight, reveals subtle shifts in surface temperature and composition. By splitting the sun's light through spectroscopy, astronomers have watched its outer layers slowly grow richer in helium, the ash of burned hydrogen diffusing outward from below. This chemical drift is another sign that the core has changed. Every new atom of helium is a silent tally mark on the wall of the sun's prison, counting down to the day it runs out of room. There is also its rotation. The sun does not spin as one solid body. Its equator rotates in about 25 days, its poles in about 35. This differential rotation stretches and twists magnetic field lines, fueling the 11-year cycle. But as stars age, they lose angular momentum through their stellar winds, and their rotation gradually slows. The sun has already lost much of its youthful spin. Measured by the slowing of its surface, it has shed perhaps half its original angular momentum. That means its magnetic engine is aging, and when that engine falters, the balance of its outer layers will shift, letting them expand as the core contracts. This is the quiet prelude to the red giant transformation. We may be watching the first notes of that prelude without realizing it. Each of these clues, brightening, core contraction, magnetic instability, slower rotation, is like a puzzle piece. Alone, they could be dismissed as normal fluctuations. Together, they form a pattern too coherent to ignore. They sketch the silhouette of an aging star wearing a mask of youth. And yet we resist the idea. We tell ourselves the sun has billions of years left. We quote the numbers as if they are guarantees, when in truth they are estimates carved from averages. Averages do not protect us. The sun does not owe us a full lifespan. So, is it already showing signs of decline? The honest answer is unsettling, possibly. It is brighter, denser, and slower spinning than it was in its youth. Its flares are behaving strangely. Its chemical layers are shifting. The evidence is circumstantial, but compelling. And the most unnerving part is that these are the only signs we could see at this stage. If the sun had already passed its halfway mark, it would look almost exactly as it does now. Calm, golden, perfect. That is the cruel trick of stellar mortality. The early stages of death look like health. The fever feels like warmth. This realization rewires how you see the sky. The morning light feels different when you know it might be the glow of exhaustion rather than vitality. The same photons that paint the clouds are messages from a furnace straining harder every year. We call it sunrise, but it could just as easily be the slow ignition of our ending. There will be no sudden warning, only this, a gradual crescendo that we mistake for serenity. And maybe that is why this question lingers so sharply. What if the decay has already begun, and we are too mesmerized by the glow to see the cracks forming beneath it? If that's true, then every solar flare, every magnetic storm, every unexpected surge in activity is more than a spectacle. It is a clue. A flare is not just a burst of light. It is a glimpse into the tension inside the sun's plasma, a crackle of strain where magnetic fields snap like overwound rubber bands. They may still fall within normal limits, but so do the first coughs of a collapsing star. The Carrington event of 1859, a colossal flare and coronal mass ejection that fried telegraphs across Earth, was long dismissed as a freak anomaly. Now we wonder if such megaflares are more common during subtle internal transitions, when the sun's layers start slipping against each other. If so, the recent uptick in powerful flares could be more than coincidence. It could be the rhythm of a heart under strain. And if the sun truly is entering that phase, the timeline to catastrophe shrinks. The red giant transformation is still far off on paper, but instability can accelerate evolution. Slight core heating speeds fusion, which heats the core more in a runaway cycle. The star grows brighter, then unstable, then swollen. What we think will take billions of years could collapse into hundreds of millions. To human civilization, that difference is everything. 1 billion years feels like forever. 100 million is a blink. Imagine building our entire species' future on a ticking bomb we cannot see. This is the mystery we stand inside. We are trying to read the health of a star from the glow on its skin, and the skin lies. By the time the surface begins to visibly change, the core's fate will already be sealed. That means, if the sun has passed its halfway point, the only evidence will be the faint clues we see now: brightening, magnetic stumbles, unusual flares. This is why astronomers keep watching obsessively, not out of idle curiosity, but out of quiet fear. Because if we wait for the sun to look sick, it will already be too late. And maybe that is the lesson hidden in its light, that stability is the most seductive illusion of all. The sky looks the same every morning, and so we assume it will always look the same. But nothing in the universe stands still, not even the star that taught us what light means. The next time you see a flare erupting on its surface, ask yourself, is it just weather, or the heartbeat of a fading heart? We comfort ourselves with probabilities. We say the sun has 5 billion years left because the math says so, because averages whisper reassurance. But probability is not a promise, it's a lullaby. History is littered with disasters that shouldn't have happened. Black swan events don't ask for permission. They creep through the cracks of our confidence, silent until they erupt. And if the sun harbors one of those hidden catastrophes, all our numbers will mean nothing. It will not care how certain we felt. It will only care about physics. We think of stars as slow, patient things, evolving on timescales so vast they seem eternal. But that slowness is fragile. It depends on an exquisitely balanced feedback loop. Fusion pushing outward, gravity pulling inward, each holding the other in check. Disturb that balance even slightly, and the serenity can shatter almost instantly. A star's life is not an unbreakable chain. It's a tightrope, and the sun could be closer to slipping than we dare to admit. One of the most unnerving possibilities is runaway fusion. Deep in the sun's core, hydrogen atoms slam together to make helium, releasing energy that pushes back against gravity's squeeze. The hotter the core becomes, the faster fusion happens. Normally, this balances out. Extra heat makes the outer layers swell, which cools the core and slows fusion. But if the core grows dense enough, this safety valve could fail. The heat would not escape quickly enough. More heat means faster fusion, which makes more heat still, a runaway loop. The core would surge in temperature, accelerating the sun's evolution by millions of years in a geological blink. It wouldn't explode like a supernova, but it could swell into a lethal red giant centuries or millennia early, boiling Earth long before we expect it. To civilization, that difference is the same as suddenly. Then there's the specter of a premature helium flash. Under normal conditions, when the sun's hydrogen runs out, its core will contract until temperatures soar to about 100 million degrees, igniting helium in a brief, violent burst. This is meant to happen 5 billion years from now. But timing in stars is delicate. If internal mixing or magnetic turbulence pulls fresh hydrogen into the core unevenly, pockets of helium ash could build up faster than models predict. A sufficiently dense helium pocket could reach ignition conditions early, triggering a localized helium flash while hydrogen still burns around it. That ignition could destabilize the whole core structure, cracking the star's equilibrium and forcing a rapid, chaotic restructuring. Imagine a second heart suddenly beating inside the first, throwing the sun into convulsions. The entire star could swell in decades, not eons, and we might not see it coming until the surface begins to bulge and brighten ominously. Skeptics argue this is almost impossible, but almost is not never. Stellar evolution theory is based on population averages, not perfect certainty. We've caught other stars behaving like rule breakers, swollen subgiants appearing far too young, or helium flashes erupting earlier than expected in binary systems. Some showed no outward signs until they abruptly changed. If our sun hides similar instabilities deep within its core, they would be invisible from the surface until they were irreversible, like a silent aneurysm building for millennia, then bursting without warning. Even more chilling is the prospect of magnetic field breakdown. The sun's magnetism is not decoration, it's architecture. The twisting magnetic fields generated in the tachocline shear zone help distribute heat and plasma, controlling the rhythm of convection that keeps the star stable. If that field collapsed or flipped erratically, convection could go wild. Hot gas could surge unevenly, stalling in some layers and overfeeding others, creating hot spots that accelerate fusion locally. The star's energy transport system would jam like an overheated engine, pressure piling up behind magnetic dams until they fail violently. This kind of internal chaos could jolt the sun into structural instability, making parts of its core burn faster while its outer layers struggle to adjust. Think of gears slipping inside a machine designed to run perfectly. One slip, and the machine tears itself apart. There are hints this danger isn't purely theoretical. Over the past century, the sun's solar cycle has grown strangely erratic. Some cycles peaked unusually weak, others shockingly strong. The magnetic field flips that drive this rhythm have shown jitter, like a clock skipping beats. Space weather forecasters have quietly debated whether this could foreshadow a more chaotic magnetic future. If the magnetic field disintegrated into turbulence, it might unleash century-spanning flare storms, or, paradoxically, lull into a deceptive quiet while chaos brews beneath. Either could signal that the sun's internal plumbing is breaking down. Either could be the first domino in a collapse we would not recognize until it was unstoppable. These scenarios seem remote, but so did many disasters before they happened. The Carrington event of 1859, a solar storm that set telegraph wires on fire, was considered impossible until it happened. The Chicxulub impact that erased the Tyrannosaurus rex came from nowhere in the cosmic blink of an eye. The Tunguska event flattened forests before anyone saw a streak in the sky. Rarity is cold comfort to the species that experiences the one. If the sun suffers a black swan failure, there will be no second chance to learn from it. We will have only one sunrise to realize something has gone fatally wrong. And would we even get that warning? Possibly not. The sun's light takes about 8 minutes to reach Earth. If the core abruptly shifted into runaway fusion or a helium flash, the first signal might be a sudden, blinding surge of radiation. No build-up, no crescendo. Just a flash of white across the sky, and then silence. The atmosphere would ignite, oceans vaporize, crust peel away in waves of molten rock. Civilization would not collapse. It would simply end, erased faster than we could scream. All our billions of years of history would blink out between one heartbeat and the next. The last thing anyone would see is daylight becoming something too bright to bear. We soothe ourselves by saying the odds are tiny. And they are. But low odds are meaningless over long enough time. Given enough years, even 1 in a billion events eventually happen. And the sun has been burning for 4.6 billion years already. The longer it burns, the more chances for chaos to find a crack in its machinery. Think of it this way. If someone flips a coin long enough, eventually it will land on its edge. Nature doesn't care how rare something is. It only cares if it's possible. This is why astronomers quietly monitor the sun's rhythms like nervous doctors. They watch its vibrations through heliosysmology, its spectral fingerprints through spectroscopy, its rotation through Doppler imaging, its flares through orbiting space telescopes. They are not just gathering data. They are watching for the slightest stutter in the heartbeat, the faintest tremor in the glow, because they know what few dare to say aloud. If something truly catastrophic begins inside the sun, we may have only weeks or minutes to recognize it. And if that day came, what would humanity do? Could we even respond? Build underground cities? Launch arcs to other stars? Hide behind shields as the sky turns white? Realistically, no. The timescales would be too short. There would be no global evacuation, no heroic last-minute fix. We would not fight the sun. We would only bear witness. Maybe that is the most haunting part of all, that the death of the sun would not be a battle. It would be a spectacle, and we would be the audience, not the survivors. This is why the black swan possibility matters, even if it feels remote, because the price of being wrong is everything. If we assume the sun is safe and it isn't, we lose our only home. If we assume it's fragile and it isn't, we lose nothing but our complacency. The first choice costs our comfort. The second could cost our existence. Which risk would you rather take? And so the question lingers like a shadow across every sunrise. Could the sun betray us without warning? Would we see it coming? Or just a flash of light, too bright to understand? There will come a morning when the sky feels wrong. The sun will still rise, but its glow will be too deep, too heavy, like molten brass instead of gold. The shadows will stretch thinner, the air will taste brittle and dry, and though the winds will still move the trees, the leaves will hang limp. On that day, the sun will have crossed the threshold, no longer the gentle anchor of life, but a predator. It will be the same star we have always known, and yet no longer ours. The change will have begun long before we notice. For billions of years, hydrogen fusion in the core will have quietly slowed as the fuel dwindled. Gravity, unopposed, will crush the core tighter, and as it shrinks, it will grow hotter. That extra heat will ignite the thin shell of hydrogen just outside the dead helium center. The sun will find a second wind, burning even faster now, pushing outward with reckless fury. Its outer layers will swell like breath inflating a dying ember. At first, it will only grow brighter. Every century, its luminosity will climb, warming Earth by fractions of degrees. The polar ice will vanish, the seas will sigh upward and drown the coasts. Then, as the oceans thin and retreat, the air will dry and clouds will disappear. Rain will become myth. The sky will harden into a pale brass dome. From space, Earth will look scorched, its blues fading to cracked browns and reds. Yet even then, the sun will only be stretching. The true metamorphosis will still lie ahead. Over the next few 100 million years, the transformation will accelerate. As the core contracts further, the hydrogen shell will burn hotter still. The sun will swell tens of times its original size, its surface cooling to a ruddy crimson even as its power multiplies. It will become a true red giant, a swollen, trembling sphere so vast that its edge will loom where Mercury now orbits. That tiny innermost world will not stand a chance. The sun's expanding atmosphere will lick it apart like frost under a blowtorch. Its iron core will melt, its crust boil, its atoms drift upward as vapor. Mercury will not even fall. It will dissolve, its orbit erased as if it never existed. Venus will last longer, but only just. As the sun's edge inflates past Mercury's former path, the Venusian skies will ignite. Carbon dioxide will break apart, oceans of acid clouds will fall as ash, and the planet will turn into a molten skull. For days, its silhouette will glow cherry red like a coal. Then it too will be drawn inward, its orbit dragging through the sun's outer gas, spiraling down like a drowning ember. When Venus touches the photosphere, it will vanish in a flash, a planet erased in seconds by the heat of its parent. And Earth will know it is next. Even before the sun touches it, the surface will become uninhabitable. The oceans will evaporate completely, leaving behind empty basins cracked into hexagonal tiles of salt. Mountains will slouch into puddles of lava. The air will become a thin veil of steam and carbon. No living thing will endure. Not even the hardiest microbes will survive the surface heat. The continents will glow faintly in the infrared like cooling iron. From orbit, the planet will look like an ember left at the bottom of a dying fire. Still, there is a sliver of hope whispered by orbital models. As the sun loses mass in its expansion, its gravity will weaken, and Earth's orbit might drift outward, perhaps far enough to escape being swallowed. It is a comforting thought, but likely false comfort. The sun's swelling outer layers will not be empty. They will be thick enough to drag against Earth's motion, slowing it, pulling it inward. Like a stone skimming the surface of a lake, our world will spiral down. Even if it dodges engulfment at first, the tides of plasma will claw at its orbit until friction wins. One day, the horizon will rise red and fill the entire sky, and the air will shimmer white-hot. Earth will touch the sun, and then it will be gone. It will not be an explosion. There will be no blast wave, no dramatic shattering, just dissolution. The crust will peel away like mist. The core will melt into droplets. The whole planet will stretch into a glowing arc and fade into the convecting plasma sea. Cities, oceans, fossils, dreams, all erased in moments. No trace will remain. Earth's orbit will simply become another layer of the sun's atmosphere, its history reduced to atoms swirling inside the beast that birthed it. The moon will outlive its parent world briefly. Freed from Earth's gravity as our planet dissolves, it will sail alone through the baking sky. For a few days, it will orbit the swollen sun as a lonely wanderer, its gray face glowing orange with heat. Then it too will soften, drip, and vanish. All the poetry humanity once saw in its craters will boil away in silence. Mars might survive a while longer, skating the outer edge of the inferno, but the red planet will not escape unscarred. Its carbon dioxide will boil, its water ice caps sublimate into space. The surface will melt into rusty glass. Eventually, even its orbit may destabilize, dragging it inward to the same fate. The asteroid belt will melt into rivers of molten nickel and stone. One by one, the inner children of the sun will fall into its arms, like moths circling back to the flame that once warmed them. As the sun swallows its worlds, its shape will become grotesque. Its surface will pulse and shudder like a wounded heart, convecting in colossal waves. It will not be the clean sphere we know now, but a trembling leviathan shedding its skin into space. Immense arcs of plasma will whip thousands of times taller than Mount Everest, twisting in tortured magnetic knots. From afar, it will resemble a dying lantern, glowing brighter even as it frays apart. And then, as its helium core grows dense enough, a final upheaval will erupt deep inside. A helium flash, the sudden ignition of helium into carbon. For a few moments, the core will burn 100 billion times brighter than the sun shines today. The outer layers will convulse outward violently, ballooning to nearly 1 astronomical unit, brushing the path where Earth once circled. The sun will be a red supersphere, so vast it will dominate the sky from Jupiter. And then, like a dying breath, it will exhale. Massive waves of gas will surge outward, carrying decades' worth of the sun's mass into space. The solar wind will become a hurricane of glowing particles rushing past the outer planets. Saturn's rings will erode into mist. Neptune's skies will brighten like dawn from afar. Every surviving moon will be bathed in deadly light. The entire inner solar system will become a blurred halo of drifting embers. It will be hauntingly beautiful, like a cathedral on fire. Inside this fading furnace, the core will shrink to the size of Earth, a blistering white pearl glowing at hundreds of thousands of degrees. The outer layers will keep peeling away until only this exposed heart remains. We call it a white dwarf, but that term hides the truth. It will not be white. It will be searing blue-white at first, slowly dimming to ivory, then ember orange, and finally to black over trillions of years. A corpse of a star, a relic, the tombstone of everything we have ever known. This is the sun's destiny. Not a sudden apocalypse, but a slow betrayal, a parent devouring its own children. Every world it once nurtured will be erased, every orbit swept clean, every trace of life burned away. And all of it will happen not because the sun hates us, but because it cannot help it. This is what stars do. They give life only to take it back. We like to imagine the future as progress. Cities of glass, ships between the stars, endless tomorrows. But those dreams exist only in the brief calm between two cosmic fires. The fire that birthed the sun, and the fire that will end it. All of human history fits into a single heartbeat of the sun's life. And when the red giant rises, that heartbeat will stop. So the question becomes hauntingly simple. Should we stay to witness our world's last dawn, or flee into the dark and survive? Would you want humanity to stand on crumbling cliffs as the oceans steam away beneath a red sky, just to see the last light of home? Or would you want us to turn our backs, to leave the ruins of Earth behind and sail outward, never to see the sun again? Because one day, the sun will rise for the last time, and it will rise not to warm us, but to burn everything we ever loved. We imagine apocalypse as firestorms and falling asteroids, but the more likely doom would be invisible. It would arrive not as a roar, but as a hum, a quiet tremor inside the magnetic field of our world. One sunrise, satellites would blink out, phones would die mid-call, power grids would sag, spark, and fail. Within hours, the global web that cradles civilization would unravel, and the cause would be our oldest companion, the sun, turning hostile not by choice, but by age. Every empire humanity has built rests on an assumption so deep we never question it, that the sun will behave, that its light will be steady, its winds gentle, its storms rare. We plant crops by its warmth, fly jets guided by satellites it powers, launch ships through space trusting it to shine. Yet the sun is not steady. It is a nuclear tempest chained by its own balance, and that balance is starting to fray. The older a star becomes, the more restless it grows. Magnetic fields tangle, solar flares sharpen. Coronal mass ejections swell like fists. One day, that restlessness could break through, and when it does, our civilization will feel how thin its armor truly is. The warning signs are already etched into history. In 1859, a magnetic storm known as the Carrington event erupted from the sun, a titanic coronal mass ejection that slammed into Earth with almost no warning. Telegraph wires burst into flames. Operators were shocked unconscious. Aurora light glowed blood red as far south as the Caribbean. And that was a world without power grids, satellites, or the Internet. Today, the same event would be catastrophic. High-voltage lines would overload and melt. GPS constellations would fry in orbit. Stock markets would freeze. Aircraft would lose navigation. Hospitals would go dark. We would be thrown back centuries in days. Yet the world would still be watching TikTok when the storm hit. And the terrifying truth, the solar cycle shows that such storms are not rare. They are inevitable. Every 11 years or so, the sun's magnetic field flips, becoming chaotic. During these peaks, CMEs lash out constantly, most missing Earth by chance. Our modern world has survived only by luck. In July 2012, a CME almost as powerful as the Carrington event crossed Earth's orbit. We were on the other side of the orbit. It missed by 9 days. 9 days from an extinction-level technological collapse, and most people never even heard about it. Now, imagine the same sun, but older, more unstable. As the core burns through its hydrogen, the sun's magnetic dynamo will falter. Its tachocline shear zone, where rotation generates magnetism, will grow erratic. Magnetic loops will twist tighter before snapping, releasing flares far larger than anything seen in recorded history. Super flares, astronomers call them. Stellar tantrums thousands of times stronger than normal flares. We have seen other aging stars unleash them without warning, burning their own corona into space. The sun could do the same as it nears its twilight, and our fragile, wired civilization would be the kindling. Picture the chain reaction. The flare arrives at Earth at the speed of light. In under 8 minutes, radio blackouts ripple across the planet. Planes over the Arctic lose contact. Rescue beacons fall silent. Then the coronal mass ejection follows, a billion-ton cloud of charged plasma. It rams the magnetosphere like a battering ram. Power grids sag under surging currents. Transformers detonate in showers of sparks. In seconds, hundreds of millions lose power. Banks freeze. Water pumps stop. Gas stations go dry. Refrigerators fail. In cities, the silence becomes loud. No hum of lights, no buzz of screens, just wind and sirens. Satellites will not just glitch, they will die. Their circuit boards will fry under the particle barrage. Low Earth orbit will become a graveyard of tumbling debris as dead satellites collide. The International Space Station crew will shelter behind water tanks, praying the radiation subsides. Global Internet backbones, dependent on orbital relays and undersea cables powered by onshore grids, will collapse. Within days, international communication will revert to shortwave radio. Most people will hear nothing at all. The human cost would spiral fast. Without power, food supply chains fail. Supermarkets empty in hours. Hospitals ration fuel for generators. Emergency services collapse under demand. In darkness, panic breeds faster than disease. Some will try to flee, but fuel pumps won't work. Airports will be silent. Skies empty. The world will shrink to walking distance again. And somewhere above the smoke, the sun will still glow. Silent, indifferent, older. What makes this nightmare more than fiction is how close it already came. In February 2022, a modest geomagnetic storm heated the thermosphere just enough to increase drag on dozens of newly launched satellites. They fell back to Earth and burned. A minor hiccup in space weather erased millions of dollars in hours. Now scale that to an aging star whose storms could last not hours, but weeks. The damage would cascade. Engineers would not have time to repair. They would be too busy surviving. And unlike the Carrington event era, our world has no slack left. In the 19th century, losing telegraphs was inconvenient. Today, losing power is fatal. Medicine, finance, food, water, all run on electrons. The average city keeps only a few days' food on shelves. Hospitals have hours of generator fuel. Your phone, your bank, your stove, your news, your family across the ocean, they all exist only because the sun behaves. If that assumption breaks, our way of life breaks with it. There is no real shield. We have satellites watching the sun, but they give minutes of warning, not immunity. NASA and NOAA track space weather, but they can't stop it. Power grids can be hardened, but only slowly, at staggering cost, and most nations have barely begun. The global system is like a glass skyscraper, gleaming, complex, and utterly brittle. A single stone through the window could bring the whole structure down. The stone is already glowing on the horizon, and this is only the beginning. As the sun ages, its instability will not just knock out infrastructure, it could choke off our escape routes. Space travel depends on precise navigation and low radiation corridors. A stormy sun would fill interplanetary space with charged particles, frying electronics and cooking astronauts. Launch windows would close for months or years. Mars colonies would be cut off. Lunar outposts would sit dark. Humanity could find itself trapped on a burning planet, watching its bridges to the stars melt away. Could civilization survive even 1 year without the sun's stability? Not the warmth, the stability. Not the light, but the silence between storms. We like to think we are masters of nature, yet every heartbeat of our digital world depends on a star we cannot touch or tame. If that star begins to die, it may not wait to kill us with heat. It may kill us with chaos first. A storm could erase the scaffolding of civilization long before the fire reaches our skin. And when the screens go dark, there will be no going back quickly. Rebuilding a global grid from scratch takes decades. Without satellites, without manufacturing, without global coordination, humanity could plunge into a dark age with the ruins of space-age technology rusting in the sun. Cities would become silent tombs of glass and steel. The night sky would blaze with aurora and be watched by no one, because no one would know what they were anymore. We think we have built something permanent, but permanence is an illusion. Our civilization is not stone. It is spider silk, spun across the void, trembling in the solar wind. And the wind is rising. So the question echoes, quiet and sharp. Could a dying sun end our civilization long before it ends our world? Could all of human history vanish because the sky simply hummed too loud one day? One day, the sun will die. That is certain. It will swell like a wounded god, swallow its closest worlds, and shed its skin across the night as a fading nebula. Long after our bones are dust, the star that birthed us will exhale its last light. But even as that inevitability looms like a funeral shadow, another question burns brighter. Must we die with it? Or could life, fragile and improbable, find a way to outrun its own creator? It is a thought both audacious and inevitable. The first fish that crawled onto land did not know it was escaping the sea, yet its descendants became us. In the same way, perhaps the first human who leaves this solar cradle will not think of it as an escape, only as exploration. But every star has a deadline, and survival demands disobedience. To outlive the sun, we must become something more than children of a single world. We must become wanderers of the void. The first step will be to build havens, self-sustaining habitats that can cradle human life even as the sun falters. Engineers dream of vast rotating stations like O'Neill cylinders, colossal wheels of steel and soil spinning in darkness, their curved horizons lined with forests under false skies. Inside, day and night would be measured not by sunlight, but by the turning of machinery. Crops would grow under artificial suns. Rivers would flow in zero-gravity arcs. These arcs could drift in safe orbits, moving farther from the swelling star as its heat rises. It would not be freedom. It would be exile, but it would be life. Beyond these shelters, bolder visions await. Imagine dismantling the entire Mercury and forging its iron bones into a shimmering shell around the dying star. A Dyson swarm of millions of orbiting habitats, capturing every last photon before the sun grows cold. Each module a world unto itself, spinning fields and seas inside fragile spheres, bound together by the ghost light of their parent. Such a civilization could endure long after the planets are consumed. It would live inside the echo of the sun's fading heartbeat, drawing warmth from its corpse. Yet even that would only delay the inevitable. When the sun becomes a white dwarf, a dim cinder the size of Earth, its light will dwindle until even Dyson swarms grow cold. Then we must make an even more impossible leap, leaving the star entirely. The gulf between stars is a cathedral of emptiness. The nearest one, Proxima Centauri, lies over 4 light-years away, a distance so vast that even beams of light need more than 4 years to cross it. No human technology has ever reached even 1,000th of that speed. Yet to survive, we must try. Some dream of giant fusion-powered arc ships, city-sized vessels that could cross the void over millennia, with generations living and dying inside. Others imagine light sails, ultra-thin craft pushed by lasers, accelerating to 1/5 of light speed. We could launch swarms of tiny probes first, then send the seeds of humanity in frozen embryos or digital minds to be born anew under alien suns. It sounds like myth, but then so did flight to the people of the Stone Age. And still, there are even wilder possibilities. Some theorists whisper about stellar engineering, taming the dying sun itself. What if we could feed it fresh hydrogen, extending its life by millions of years? What if we could move Earth outward using gravity-assist slingshots, keeping pace as the sun swells? Even proposals like the Shkadov thruster envision tilting the sun itself with a vast orbital mirror, slowly steering the entire solar system towards safer regions of the galaxy. These ideas hover between genius and madness, but so did every great leap before it. Fire once seemed impossible to tame. So did the sky. And yet, the true challenge may not be technological. It will be emotional, psychological, existential. Because to leave the sun behind is to leave behind the only definition of home our species has ever known. Every word, every myth, every childhood memory was shaped under its warmth. It has watched our first breath and will one day watch our last. How do you abandon a parent even to save your children? Perhaps the answer is that you don't. You carry it with you, not its body, but its fire. In the dark between stars, far from the sun's glow, our descendants might light miniature suns, fusion reactors blazing inside their ships, casting golden dawn across alien skies. In those tiny flames, they would keep the memory alive. The light would be new, but it would carry the same purpose: to hold back the night. In that sense, they would not be escaping the sun at all. They would be extending it, becoming its continuation. Not children fleeing a dying parent, but its legacy, burning onward. This is the paradox at the heart of our fate. We are made of stardust. Every atom in our blood and bones was forged in a furnace like the sun, born from the deaths of ancient stars. We are living memorials to their fire. The sun is not just our power source. It is our ancestor. To survive it is to honor it, not betray it. It gave us the tools to leave: curiosity, defiance, imagination. We may never repay that gift, but we can carry it forward. And maybe that is what truly matters. Not whether we last forever, nothing does, but whether we dare to try. Whether we light the next torch before this one goes out. The universe will not mourn the sun when it fades. But if something born of its fire goes on, if human voices echo around another star, then the sun will never entirely die. Part of it will be laughing in distant oceans, whispering under alien trees, singing in air it never touched. So yes, one day we may leave this star. We may thread the darkness and find new suns to circle. We may outlive our origin, but even as we do, we will always belong to it. Because the truth is simple and beautiful and unbearably fragile. We are the sun dreaming of not ending, and if we succeed, if we survive, then its dream will come true.